Now, significant figures are one of those things that we kind of hammer you on here in general chemistry and in other sciences as well, because it's important. We don't want to get caught overestimating and overindulging some of the errors that are associated with measurements. When we attach good significant figure rules, we can gain confidence in measured values. So take, for example, I've got an object I weigh on two different balances. First balance says that the object weighs 3.59 grams. The second object says that it weighs, or the second balance says the object weighs 3.5882 grams. Now, both seem to be saying close to the same thing. In fact, if I round the second balance up to the same number of decimal places as the first balance, I would get the same value. Which one of those do we trust more? Well, it'd be the second balance because it's got more decimal places. It's got more overall instrumental precision. I have more significant figures in that second balance. And so that increases my confidence. That tells me, okay, that's probably more close to accurate in terms of what the actual mass is. So the more significant figures that our measurements have, the general confidence, certainty that is associated with those measurements increases. But we can't just simply invent significant figures in order to increase confidence. We'll always be limited by the object, the instrument itself. So how do we go about evaluating how many significant figures a particular balance or a particular measurement tool gives us? Well, there are some guidelines that can help us. Most of the guidelines regarding significant figures fall around this general idea. The general idea is that when I have a measured value, non-zero numbers are significant, and zeros are the things that we have to watch out for. What kinds of things do we have to watch out for with regard to zeros? Well, first of all, if a zero is starting a number, those zeros at the beginning of a number are never significant. What we call those zeros are placeholder zeros. And they do things like tell us that our measurement here is a really small number, 0.000000559 meters. Okay, that's a really small number. That's 5.59 micrometers, or microns. Small. If I don't have those zeros there, this number takes on a whole different meaning. 5.59 microns is way different than 0.559 meters. One is thinner than a piece of paper. The other one is about, about 1.5 feet in length. Very different from each other. So placeholder zeros like this, their only purpose is to hold the place, to make it so that we are showing the correct value of the number. They don't contribute to significant figures whatsoever. When we have zeros after a non-zero number, they tend to be significant, with the one notable exception. So if I have a decimal point, let's take this value again, 0.0000059. If at the end of that I had a couple of zeros, that would be significant. This is showing additional precision of the instrument compared to this one. So kind of the same kind of thing that we saw in the previous slide. In this example, I had 3 significant figures. In this one, I have 5. But what if I don't have a decimal point? What if I have a number like this? $121,000 grams. Well, it's really difficult to know whether or not those are significant or not. Our general rule of thumb is that if we don't see a decimal point, zeros like these would be placeholder zeros as well. It would not be significant. We would say that this particular measured value had 3 significant figures, just these 3 right here. 1, 2, 3. Problem is that's not always the case. Sometimes those zeros are significant, sometimes they are not. This is when it is best to use your scientific notation, because scientific notation will always show the correct precision, because every digit in scientific notation is a significant digit. Important thing to know. Make sure that you've got that written down somewhere. Every digit in scientific notation is a significant digit, which means that you need to handle those properly. So if I wanted to express this number with having 4 significant digits, I would need to make that adjustment accordingly in my scientific notation. It would be 1.210 times 10 to the 5th grams in that case. That would show 4 significant digits because my scientific notation always shows the correct number of significant figures. In that case, 4. Finally, if we have zeros between non-zero numbers, they're significant. So again, the only zeros that we have to worry about are the ones that either begin a number and are never significant, or the ones that end a number, and depending upon the circumstances, whether there's a decimal point, whether the scientific notation is present or not, those may or may not be significant. Again, scientific notation really helps to clarify that significance. Now, what if I have to do calculations? Well, the general rules for calculations with significant figures are that how you handle them really depends on what kinds of mathematical operations that you're doing. But before we get into those specifically, there are some general guidelines I'd like to give you. First of all, when it comes to rounding in calculations, try your best not to do so until the very end. Limit the number of times you have to round a number. Because every time that you round a number off, you are introducing a little bit of error. So let's say that you had a 4-step calculation, and every step along the way, you're rounding off the number, rounding it off. Well, in those 4 steps, you're doing 4 different roundings. You're going to end up with far different answer, at least most of the time, than this person who does all 4 of the calculations in a row and then rounds at the very end. Which one of you are correct? Well, the person that did it all in one calculation step actually has the more accurate result. Every time you round, you introduce error. Introducing error makes your results a little bit less accurate, a little bit less trustworthy. Second guideline, there's what we call the weakest link principle. And what the weakest link principle says is that when it comes to rounding, you're going to use the measurement that has the fewest decimal places or significant digits when you do that rounding. The other guideline here that you'll want to add is something that we call the rule of fives. If the number next to the last significant digit is 5 or greater, you're going to round up. If not, if that number is less than 5, then you round down. Really simple. I mean, this is the kind of rounding discussion that you've probably had since upper elementary school. 5s and up, round up. 4s and down, round down. So hopefully shouldn't be that complicated for you as you're doing those calculations. Now let's look at these two here. When it comes to mathematical operations, there are two sets of rules. One that abides when we are adding and subtracting, one that abides when we are multiplying and dividing. So for adding and subtracting, here's where decimal place matters the most. When we are doing any kind of rounding, we want to pay attention to decimal place when we add and subtract. So the easiest way to show this, I've got an example here, 10.011 plus 11.01. If I put it into my calculator says that the sum of those two is 21.021. Now, based upon what I added together, I can see that this 1 here at the end was an uncertain digit in the first measurement, and this 2 was an uncertain digit in the second addend. Our weakest link principle tells us that we are going to round to the value that is the leftmost decimal place that has an uncertain digit in it. That would be this 2. So using our rule of 5, 1 is less than 5, we're going to round down. 21.02 is our answer. In our second example, and then again, this is where things get a little bit more complex. 19,900 minus 375. On the surface, if you were following this from a math problem perspective, you would look at this and say, okay, I just subtract the two values, 19,525 is my answer. Problem is, we have to assume that these are measured values. And as measured values, significant figure rules apply. Since these two zeros are ambiguous, we have to make the safest assumption, and that safest assumption is that they are non-significant, which means that the last significant digit was that 9 in the 100ths place, as opposed to this 5 in the ones place. Our weakest link principle says we need to round to the leftmost uncertain place. That 2 means we're going to round down. So that's where we get 19,500. Now, the other thing to make note of here, we cannot lose sight of the values themselves. And what I mean by that is this. I've seen it happen on a number of occasions where a student does something like this and correctly identifies that those zeros are insignificant and mistakes it for meaning that they are not real. And so instead of giving me an answer of 19,500, they give me an answer like 195, where they just completely chop off those last two values. That's not what happens. Now, if we want to avoid ambiguity, the best thing that we should do here is convert that into scientific notation so that there is no discussion, there is no issue there. 1.95 times 10 to the fourth would be the correct scientific notation. That way we can be certain there are only 3 significant figures there, as opposed to 4 or 5. So adding and subtracting, in my mind, that's the harder one because decimal places are a lot more difficult to keep track of in general. When multiplying and dividing, it's a little bit easier because all we need to keep track of are the number of significant figures. So in this example, I have 3 significant figures in 9.19. I have 4 significant figures in 3.171. I have 2 significant figures in 1.0. That 0 is significant because it follows a decimal place after a decimal point after a non-zero number. I look at my 3 measured values. The weakest link principle says that I go with the one that has the fewest significant figures, which means even though my calculator juts out 29.14149, I round that to 2 significant digits. That gives me a total of 2. 29 is the correct answer there. So again, multiplying and dividing, far more simple than adding and subtracting. In terms of getting the correct number of significant figures. Now it's going to feel weird at first to basically chop off a whole bunch of numbers. But just because your calculator generates them doesn't mean that they're significant. You have to use your brain, you have to use your guidelines to generate and make sure that you are determining which numbers are significant, which ones are estimated, and which ones don't matter. And so in this case, 29 is the correct answer. 9 is the estimated digit. Everything else after that really doesn't matter at all. All right, we'll end with one last final example, just as a review problem. I've got 3 measurements for 3 different nails here. What I want to do is this. We're going to do 2 problems here. What is the total mass of the 3 nails? And I'm also going to throw in what is the average mass of the 3 nails. So again, go ahead and hit pause here. Try to do this one on your own. Come back in a couple of seconds and I will work out the problem. You can kind of check yourself against me and see how you did. All right, so in doing this problem, we're going to find the total mass, I'm going to need to take those 3 masses and add them together. If I do that, 13.47 plus 13.43 plus 13.4653, I end up with a total mass, according to my calculator, of 40.3653 grams. Now, before I go ahead and click that one into my homework, I would want to look at it and say, did I do my significant figures properly? And so, since I am adding here, I need to look at where do those numbers come from. And so I can see that nail 1 and nail 2 are both known to 2 decimal places, whereas nail 3 is known to the 4th decimal place. Keeping with my weakest link principle, I'm going to round that 6 either up or down. Since 5 is next to it, I'm going to round it up. And so my value here is actually going to be 40.37 grams. That is going to be what I record as the total mass of those 3 nails. Now, that sounds kind of absurd. After all, that is less, or excuse me, that is more than what the calculator said those three values were. But what this is accounting for is that there is uncertainty in those first two nails that was not there in the third nail. And so to account for that uncertainty, I have to include that second digit, and that ends up meaning I have to round it up as a result. Now to do the average mass, remember average is just the total mass divided by 3. If I take that total mass and divide by 3, my calculator spits out 13.4551. What of that do I keep? Well, this is a division. You may look at this and say, well, I need to divide by 3. Or I'm sorry, I need to have one significant figure because my value 3 here only has one significant digit. Well, remember, this value is exact. There were exactly 3 nails that we added here. Exact numbers do not factor into significant figures. So what I really need to do here is the number of significant figures that I kept at the beginning come out at the end. So 1, 2, 3, 4. This 5 is the last significant digit. I'm going to look and see that the 5 next to it is going to cause me to round up. And so the average mass is going to be 13.46 grams. So that's all for this particular lecture.